Welcome to the next lecture in the bridges series. Here we will learn the absolute basic of bridge engineering, and today we'll discuss the bridge support. We'll learn about the three major types of bridge support: abutments, piers, and pylons. We also mm, touch the foundations like geotechnical conditions, shallow and deep foundations. Most of these topics, however, are already a part of the lectures about geotechnics, so it will be just a reminder. So as I mentioned in the introduction, we distinguish three basic types of bridge support. These are abutments that support the superstructure at both ends of the bridge and connect the span structure with the embankment at the road access to the bridge. These are very characteristic elements that are not found in other types of construction works. The second type of support are piers. They constitute an indirect support of the superstructure between the abutments and also define the division into spans. Hence, in the case of this example bridge, we are talking about a multi-span bridge. In the addition, in suspended or cable-stayed bridges, we're going to have pylons or towers which are usually very high and extend above the level of deck, while the piers are always under the deck, under the span. Let's start with the abutments. It should be it should also be remembered that the vast majority of the abutments in the bridges, in fact, during operation, are invisible. It is covered by an embankment cone and can only be fully seen during construction. Here we see a very large wing of the abutment, which will soon be covered by the soil of backfill and will be no longer visible. How much remains visible can be seen on these axonometries. Abutments ensure vertical support of the load-bearing structure at both ends of the bridge. They connect the bridge with the access road. In the area, there is a certain transition zone between the road laid on the span structure and road laid on the embankment structure. The characteristic shape, especially the wings, results from the fact that the task of the abutments is to additionally maintain the slope of the road embankment on the access roads. The embankments ends in the area of the abutment, creating a tapered cone of soil. Abutments can be divided according to shape. They are closed with massive bodies or opened in the form of pile or rib abutments. They can also be divided due to the connection of the abutment body with the load-bearing structure. So they will be frame or with a span supported by bearings. The next classification is due to the type of foundation. And here we have shallow or deep foundation. And finally, we can divide them due to the arrangement of the abutment wings, which can be parallel or oblique to the axis of the road on the bridge. Here we see several types of abutments by shape. So they are closed with massive bodies, in which the body is open in the form of shields of piles. The splice of these piles is usually a footing board of the support that supports the span. Abutments belong to very old building structures that were domain of army engineering troops in the past. It must be remembered that even in the 19th century, bridge engineers were usually officers in the army, and bridges were of strategic importance. Hence, the names of abutment components are somewhat military and quite old. Going from the bottom of we have a foundation. Then we have the abutment body, which can be massive or open. It's just massive in this example here. Next, we have a bearing bench on which there are bearing pads. Bearings are placed directly on them. The girders of superstructure usually rest on bearings. Behind the bench is a back wall, sometimes called a gravel wall, as it serves to keep the backfill behind the abutments so that it does not spill onto the bearings and face of girders. There are also wings on both sides, whose task is to maintain the embankment slope. Note that behind the body of the abutment and the so-called abutment chamber, uh, it is limited on three sides by the body and two wings. It is usually filled with a backfill and covered with an approaching slab, which we will talk about later. Let's look at the same abutment, but in the three orthogonal views in the section, with the sections. So we have at the very bottom the foundation, which may be a solid rectangular block or may have a C-shaped projection. This depends on the need to support the wings, which often protrude far beyond the body and may need extra support. The heaviest and largest body of the abutment rests on the foundation and are usually over a meter thick. The top of the body is a bearing bench with a few bearing pads. Behind the bench is a back wall, approximately 40 centimeters thick. On both sides of the body there are wings which sometimes have such a triangular shape. They can also have their own foundations or they are cantilevered. And we have here the approaching slab yet, which on one side rests on the back wall and stays inclined in the embankment soil, covering the abutment chamber. Now an example of an unfinished abutment with a view from the backfill. You can see the body, two-sided wings, and a back wall on which the approaching slab will be placed in the future. In this photo, we see more precisely the wing. Closer to the body, it has a part fixed with its own foundation. The foundation is, of course, already covered and invisible. At the end, there is a cantilever part of the wing with a characteristic triangular shape. The adoption of the abutment type, whether it is to be open and closed, is always the result of looking for a compromise between the size of the abutment and the length of the span. In the case of open abutments, the edges of the road embankment's cones are right next to the obstacle, and the abutment's walls are already at the distance from the gauge, from railway lines. It is then possible to widen the obstacle, an example by increasing the track gauge or adding a new track or a lane under an overpass. It's just that the horizontal line underneath is bigger. The abutments are then smaller, but a longer span is required. However, this is not always feasible. In the case of closed abutments, the abutment's walls are already next to the obstacle, and it is practically impossible to widen the road or to increase the track gauge. The dimensions of the abutments are larger, and it will be necessary to use more material for them. But in turn, we will have a shorter span, which should translate into lower costs. Hence, we are looking for a compromise between the costs of abutments and spans, but with a certain assumed functional requirements and throughout the entire life cycle of the of the bridge. Abutments can be differently related to the chassis. In the abutment with bearings, its structure is independent of the span and there is an expansion joint usually. The span rests on the body by means of bearings placed on the bearing pads. Thanks to the bearings, the designer can control the freedom and direction of deformations and displacements of the span, but also the values, position, and direction of the forces transferred to the abutment. The frame abutment, on the other hand, has a body monolithically connected to the span's load-bearing structure. There are no relative displacements between the span and the abutments. However, thermal interactions generate internal forces in the span and abutment. The influence of passive earth pressure behind the abutment wall is also revealed, which also affects the span and not only the abutment. This solution is usually used in shorter and single span bridges. Now a few examples of the most common types of abutments where the span is supported on bearings. Here the span is in the form of a concrete slab structure. There is already a beam and slab structure of the span and as a result a slightly thicker body of the abutment. The girder enters the bearing bench much deeper. Here again we have a slab beam span, but with much higher girders. In variant B or option B, there is even a special chamber behind the front of the beam, which can be used to inspect the technical condition of the bearings and expansion device, expansion joint. This solution is used in the case of high girders. Here again, a solution used for narrow spans, such as are found, for example, in pedestrian bridges. Usually, there is no transition plate, no approaching slab anymore. Abutment wings work like retaining structures. They protect the abutment of the abutment chamber and the road embankments against slipping. The wings the wings may have different orientation with respect to the bridge axis. They may be parallel to the axis of the bridge or they may be inclined to the axis. Uh, the way of mounting the wings in the body of the abutment may also be different, either cantilevered or freely supported or continuous. A few examples of wings. First, the large dilated wing. It is so large that it requires support on its own foundation. A dashed diagonal line indicates the outline of the fill cone, the embankment. Below this line, the wing structure is simply covered by the soil. The thickness of the wing wall varies by ellipse and bounds. This wing is also supported on its own foundation, but there are no expansion joints. The cantilever overhang is greater than and the wall thickness varies smoothly. Here, however, we have a wing fully cantilevered to the abutment body. In this case, it is a frame bridge without a bearing. The wings can be connected to the body of the abutment in different ways, and here are some examples. In the upper ones, the bearing bench and the bearings are exposed. In the lower ones, they are masked with a wing wall. A few more unusual solutions for abutments, from massive to more slender and with light shelves up to pile abutments of various heights and shapes. As the abutment chamber is limited on three sides by the walls of the abutment body and two wings, proper drainage is essential. The possible displacement of the soil by hydrostatic pressure must be reduced. It is also necessary to control the erosion of the road embankment slopes on the cones around the abutment and to reduce the plasticization of abutment chamber backfill. Water flowing down the escarpment can seriously damage the bridge. It happens by washing out the soil covering the abutment. Therefore, the slope cones around the abutment should be properly secured. It is done by strengthening steep slopes with stone, paving, or concrete facing. It is assumed that the inclination of the slope in the ratio 1 to 1.5 does not require strengthening and, and that such a slope may be covered with grass. As the walls of the wings act as retaining walls, solutions known from the construction of retaining walls are increasingly used to make them, especially in places where there is not enough space to form gentle cones and slopes of the embankment. So in cities or at the diagonal intersections with an obstacle, here we see examples with reinforced soil and stone gabions. Here's the use of geotextiles and geogrid. Here are more examples of retaining walls being an extension of the abutment wings. So there are reinforced soil retaining walls with metal strips embedded in the ground and all abutments made of soil and geotextiles. Here we see examples with a concrete facade anchored with a geogrid, or even pillars made of geotextiles reinforced with geotextiles. Retaining walls and wings can also be made of sheet piling in the form of Larsen sheet piles. At this level of education, we will not design and calculate abutments. I invite you to the bridge specialization on the master's degree. Now just a brief overview of the problems that apply to this structural element. It is a verification of the stability uh, for movement, rotation, and shear of the soil layer. Another example of an untypical abutment with a chamber for inspection of bearings and expansion joints and a partially supported wing. First in the side view, and now the same abutment in the longitudinal section. The second group of bridge supports are piers. The pier provides vertical support between the abutments and has two primary functions: to transfer vertical forces, vertical reactions from the span to the foundations, and to absorb horizontal forces or horizontal reactions acting on the span. It can be caused by wind, temperatures, fluctuations, or vehicle braking or accelerating. The piers can be divided according to the shape. We have full or bore, empty inside with holes, with rectangular, round, and polygonal shapes. Then, due to the transverse arrangement, they can be singled or multi-pillar, cap or shield-shaped, or because of the connection to the span. And they can be fixed in the span, and then the pillar is the leg of the frame. Or it could be cantilever when there is a bearing on the pillar head. Here we see typical cross sections of pillars. At the top of the pier, there are viaducts in the dry terrain without water courses. And at the bottom of the piers, bridges in the rivers or in floodplains, where the streamline shape and resistance to ice pressure are more important. In the transverse arrangement of the pillars and rivers, we usually use massive sawmills. They should be narrow in cross-section and streamlined in shape. As a result, they provide minimal resistance to water flow. In urban areas, we use columns with a widened T-type head or a cap. This solution is used when there is no space for adjacent columns. They usually support lighter steel or prefabricated spans. Frame supports are used for wider bridges. Uh, the cap at the top of the columns forms the frame. The posts, the columns can be round, oval, or rectangular in the cross section. The most commonly used type of such a pillar is the system with two round columns. We can have various support schemes for the span. Monolithic, when the column is fixed in the span and in the foundation. Cantilever, when the column is fixed in the foundation and there is a bearing on the head on which the span rests. And the rocker arm, when the joint is at the bottom and top of the column. However, this solution is rarely used anymore. Some examples of different piers. Here we can see shield piers. Here are columnar piers, oval or round. The bottom is fixed in the foundation. In one case, the column is also fixed in the support cross member of the span. The others have bearings on the head. For high pillars, full cross-section is no longer used. The interior is usually chambered and there are stairs for inspectors, bridge inspectors, or even elevators. The pillars on the city bridges also have an aesthetic value. Therefore, they often have to be refined in terms of their architectural form. Two examples of shield pillars, the slab superstructure and beam slab system, and another two with columnar type. The last group of bridge supports are pylons used in suspension and cable-stayed bridges. And the pylons are the most visible structural elements of these long structures. Uh, they strongly protrude above the span and are visible from many sides. Pylons give such a bridge its own unique character. They create a, in fact, they create a composition that is remembered as the image of the bridge. The main structural function of the pylon is to transfer forces from the weight of the bridge, vehicles, wind, and other reactions to the foundation. The forces and the span are transmitted by the suspension members or hangers. A secondary important function is that the pylons create the character and the main theme of the bridge. The type of pylon depends on the shape and form. So we have single post pylon, type H or A, or in diamonds. The material used to build the pylons is most often concrete. More rarely, they are steel or composite. Examples of the pylons of the first suspension bridges. On the left, Clifton Bridge with a chain span and pylons referring to Egyptian architecture. On the right, the Manhattan Bridge and its neo-Gothic pylons. The modern single-pillar pylon of the Stonecutters Bridge in Hong Kong. The pylon is 293 meters high, and in the lower part, it has a cross section of 24 by 18 meters, so larger than the volleyball court. It is a double steel jacket filled with concrete. Several other modern pylons. On the left, the Millau Viaduct in France. In the center, a suspension bridge in China. And on the right, the Świętokrzyski Bridge in Warsaw. Pylons of large suspension bridges can take the shape of rectangular steel frames. On the left, two similar large bridges, the top, the Golden Gate, and at the bottom, the bridge in Lisbon. On the right, the Elizabeth Bridge in Budapest, the pylon of which is supported by a rocker arm and its enormous joint is visible. For the construction of tall concrete pylons, sliding formwork is most often used. Finally, I'd like to discuss the issue of bridge supports foundations. Before starting the design of the foundations, the geotechnical conditions of the substrate should be recognized. The stratigraphy under the ground surface is determined with experimental determination of the properties of the soil layers. The evaluation of the obtained data during geotechnical tests serves to provide a proposal for the foundation of the bridge. Geotechnical problems may have an influence on the final type of foundation, like direct, indirect, shallow or deep, bearing capacity, groundwater level, the bridge structure itself, and the adapted static pattern. In fact, most of the bridges and viaducts fall into the third highest geotechnical category, which results from the complexity of the ground conditions, soil conditions, and the structure of the facility. Geotechnical field work can be carried out by drilling methods, an example drilling, soil sampling, rock coring, by recording geophysical features in the well. We can use conical probe testing, we can do excavations and research, or use geophysical assessment techniques. For the testing of the substrate, however, drilling methods are most often used. Unfortunately for bridges, we rarely have comfortable conditions, and we are forced to drill on water or in other difficult terrain. Here I have an example of geotechnical profile that was used to design foundations for the Stonecutters Bridge supports in Hong Kong. As you probably remember, we have two basic ways of building foundation, shallow and deep. Shallow foundation is used when the foundation depth is smaller than the foundation width. In bridges, in the case of shallow foundation, the most frequently used forms are shallow a foot or a bench. More rarely, they are plate or frame. Shallow foundations can be used with sufficient load-bearing capacity of soil on racks, or when there is no risk of water washing or when the soil strengthening is provided. In the event of a risk of washing, the foundations can be protected with steel sheet piles. Here we have the three common foundations in bridge supports with single footing for columns, of course shallow foundations with footings for walls and shields, and mixed solutions used under many nearby columns. Here's an example of a viaduct with shallow foundations, but with their protection with sheet piles due to the limitation of excavations in the immediate vicinity of the railway tracks. It was also necessary to replace the soil. However, deep foundations are used much more often in bridges. The depth of such a foundation is already greater than the foundation dimension in the plan. They are used to lean on a deeper and stronger layers of soil or even on rocks. The layer below the surface are usually too weak to carry over the reaction, or it is simply a more economical solution because deep foundations usually covers a smaller area than a traditional foundation. It can also withstand greater vertical forces and can resist tearing as well as transfer greater horizontal forces. In the case of deep foundations, piles in the form of slender structural elements are used, which are driven into the ground by various methods. Wells in the form of monolithic concrete laid in a drilled hole, caissons created by lowering prefabricated elements, selecting the ground under them, removing the ground under them. We also have anchors or foundations for transferring tensile and horizontal forces. More and more often in bridges, slurry walls are also used, which consist in filling a narrow space excavation with concrete in which the reinforcement was previously placed. As I said before, piles are slender structural elements that we introduce into the ground using various methods. They can be formed in the ground in casing pipes such as Franke, Vibro or Alcon, or molded into the ground in drilled holes. Here we have CFA, Starsol, PCS or CFP methods. We can also use other methods of piling by drilling, hammering, pressing, screwing, or injection. The material used for piles can also be different, such as wood, concrete, steel, or composite. I mean the composition of steel and concrete. Here we can see the cross-section of concrete, steel, and sheet piles. We use micropiles anchors and soil nails to transfer the tensile and horizontal forces. Here we can see an example of mounting an arch bridge over the express route S1 road in Bielsko-Biała. A few examples from the foundation works of bridge supports. We see an example of a shallow foundation under a multi-pillar, a multi-column pillar. DSM column, an example, deep mixing of soil with cement. Continuous CFA piles and precast driven piles. Here we can see the process of forming large diameter piles, which have a diameter of 0.8 to even 1.8 meter. The pile heads are crushed and the protruding reinforcement is connected with the reinforcements of the cap, which is the basis for the columns, for the pillars. Here we can see the driving process of precast reinforced concrete piles, which have a square cross-section of 30 to 60 centimeters. Drilled piles without CFA type cover, the diameter of these piles ranges from 40 to 80 centimeters. And finally, the embodiment of the DSM column, which uses a cement slurry mixed with soil. The diameters of these columns are from 60 to 120 centimeters. We will see now foundation works which were done a few years ago on the construction of super long viaduct along motorway A1 from Gliwice to the Czech border. This bridge is almost 400 meters long and provides the motorway over the lake. Here we can see the construction works with drilling the large diameter piles. The drilled soil is removed from the hole, preparing an empty space for reinforcement. Here's the process of concreting the holes, concreting the piles. That's the terrain after construction works, after foundations works. Here we can see the heads of piles, which are crushed just to reveal the reinforcement. This reinforcement will be connected later with the reinforcement of the cap of foundation. Here we can see the load test of piles. A reinforcement is welded to the frame and pressing jacks are prepared for test. And ready cap of piles with sticking pillars. Every lane of this bridge has piers consisting of three columns. And the superstructure is already laying on the bearings, and montage assembly is done with weldings. Now let's look at some examples of foundation works on this bridge. First, forming large diameter piles. You can see the piling machines and the baskets of wound reinforcement of piles. Here you can see the pile heads after the excavation. We are actually in the middle of the pond, so sheet piles are driven around the trench and must be properly stretched. The pile heads are then crushed to reveal the reinforcement. The piles are subject to a trial load. Mm, a steel frame railing structure is attached to the exposed reinforcement. The piles are pressed into the ground by means of actuators pressed against the frame, checking the bearing capacity. After the reinforcement is laid in the pile cap, the column reinforcement is installed. The formwork for round columns is a special repeatable formwork. Concreting of high columns is staged and the reinforcement is continuous. Thank you for your attention, and I invite you to the next lectures in the Bridges series. We will learn about the construction of bridges with concrete and steel girders.